So this presentation is called Performance Considerations for Optimal Aurora Utilization, though it doesn't contain the key word that was supposed to be in there. We decided to remove it for unknown reason to me. I will be talking about messaging. I will be talking about MPI. Basically, I'm trying to summarize some knowledge that performance engineers, and some of them are here, contributed significantly to this presentation, accumulated during the last couple of years when Aurora is working on the floor at a significant size, which is bigger than what we previously had with Sunspot. So I have summarized certain knowledge that we gain into this presentation. I think it's going to be useful to all of you. This is a review and expectations from this presentation. As I said, I will be mostly spending some time on messaging and less about those things which are written in documentation for Aurora. For completeness, I put the link over here. I will not be talking about how to program the machine because we have significant number of presentations about it. Though I will illustrate all the examples using simple C, OpenMP, and MPI only. I will start from the initial startup of the environment. I will say a little bit about the nodes hardware just to refresh people's understanding of what we have in our position during the use of Aurora. I will say a little bit about runtime identification, settings, mapping, binding, everything which you expect to see on performance engineering talk. I will show some results, though I should tell you that the benchmarks very much depend on how you run them, and therefore there need to be more considerations about it. So when you come to our machine, you are supposed to look at which compilers you use and what environment you have. As always, this slide has been updated 1 week ago and already got outdated. The reason is known. On Monday, we have made significant change in the environment. So every version that you see here is already old. And if you start repeating the same thing that I write here, you will see a different set of modules. But that's okay. At least you will know what to expect. And as you already know, we use modules in our environment to set up users. You may see certain modules being default that you can see here from module restore module list commands. I strongly recommend to use module restore at the beginning of each session so that you know what you've been doing and so that you do not have inconsistency in your modules left from previous activity or from other means. We are currently using the MPI wrappers, which are part of MPitch installation from Intel version of MPitch. We are not using Cray MPI, even though it is available. We are not using Intel MPI, which is a commercial version of MPitch for Aurora, which also exists. We do not use those versions. We are using a special Aurora version of MPitch, the one which you can have through your modules in optimal version MPitch/opt, currently version 4.3.0 for this presentation. Or you have a debug version if you need debug symbols. The key point of the slide is to know what do you do with your compilers and which environment you will be using. Keep in mind that you need to have only those modules that you use. I strongly recommend do not use all modules that you can have available in the system. Use only those which you want to use. When I come to the machine for the first time, particularly when I come to the machine for the first time, I'm trying a usual hello world program. I'm trying to compile the code, I'm trying to run it. I do not try to compile my 7,700 line package and then try to understand why it doesn't run. I use MPI hello world, which is just MPI init, MPI finalize as simple as possible. I compile it with the default compiler, and I'm trying to run it to make sure that the compilation works correctly. If everything works that way, then the chances are that you're doing the right thing. If you don't do this first time compilation check, then the errors that you may have in your environment will accumulate. So it's better to not do that. We have a lot of places where we have advertised the topology of the node. I put this for the reference because I will constantly refer to certain namings and conventions. On Aurora, every node is a dual socket CPU with a set of memories, a set of interconnects, and a connection between the two sockets. As you can see here from this slide, each socket has 52 core CPU attached three GPUs, which are obviously Intel GPUs. I don't go into details of this. Over PCIe Gen 5, we have 4 NICs, which are HPE Cassini NICs, 200 gigabit, connected to PCIe Gen 4, and therefore to connect to PCIe Gen 5 CPU, which is Sapphire Rapids, obviously, you need to have a PCIe switch, which is here on a slide as well. So when you need to move data between the GPU and the NIC, you are passing through the switch. That's an important piece. I will say a little bit about it when we come to the benchmarks. Each socket has a DDR5 memory, 512 gigabyte, and high bandwidth memory, which is 64 gigabyte. The high bandwidth memory is placed directly on the socket of a CPU. The DDR5 memory is external. The sockets are connected through UPI bus, which is only 48 gigabytes a second. Why only? It is because there are ways of significantly increase the bandwidth when you need to transfer data in between the sockets. Z-links are those links which are connecting each GPU with each other GPU on a node. Using Z-links can be done either automatically or as a programmer you can use level 0 to do so. I am not coming into this way of doing things, though I will mention when Z-links are used under the hood when MPI is called. And I already mentioned PCIe switch could be a bottleneck, and it is a bottleneck in many cases, and I will show when we have identified that. One piece of terminology. If you are coming from a programming side, if you are running the applications, if you are asking the nodes allocation from a batch system, we use PBS here, then you are operating by a term node. This is a node. This is the smallest piece which is allocated to you as a user by the batch system. If you come from the operation side, you are mostly talking about the hardware, the real pieces of the silicon soldered on a board. The board is usually called the board is usually also a node, identical, the same, but people from operation side call them blades. So if you hear that people say something about blades, they actually mean a node of a specific location. It was very confused to me when people were saying blades, because I'm from programming side. I used to call nodes, not blades. A very important piece. If you have a picture of this node in your mind, you would understand that your application should come to those pieces of hardware which are located close to you. Locality is an extremely important piece. How to create locality in your application is what's about this talk. So I will show you how to do certain things. But locality is a key piece to reach performance on our machine. A little bit about the topology of a CPU itself. This picture is probably even better than my description. The picture is taken from the documentation. We usually have the two sockets numerated 0 and 1, and each socket has 52 cores numerated 0 and 51, and each core has two threads, thread 0 and thread 1. But from the Linux perspective, which is the operating system we are running on the node, the cores are usually considered as CPUs, and therefore the threads are also considered as CPUs. So we have the cores increasing over the socket first, then we come to the next socket, then we come to the next thread, and then we come to the next thread to the next socket. So basically, threads 0 of each core numerated first, threads 1 of each core numerated last. That's what the numeration we are using here. And as documentation says, we also have the 3 GPUs attached to each socket, and the socket 0, as usually expected, has GPUs numerated 0, 1, and 2, while socket 1 has GPUs numerated 3, 4, and 5. It seems to be obvious, however, there are machines which are not doing that way. So it's good to know the exact numeration so that you don't get confused later. You also know that each GPU has 2 tiles, and there is numeration of those, and there are ways of using those GPUs in a certain way as a full device or a sub-device, and I will touch it a little bit later. So the PBS, of course, the PBS is a very complex system, and it would probably take another presentation to cover everything which PBS provides you, but I just want to say a few things which are very much relevant to performance. One of those, which not very many people actually know, that you can always ask the specific node or set of nodes for a repetitive study, for particularly performance study on our machine. So if you submit the request for 2 nodes, you can specify which nodes you want to get allocated. But practically, you can have as many nodes as you want. Of course, having more than a handful of nodes becomes not very much practical for you. So you need to script things. But that's the possibility, and I strongly recommend using it if you want to have repeatable results from your study. The second consideration for those people who need to have very close allocation of the nodes, particularly for collective communication operations, for those people who need to have very high bisection bandwidth for your small subpartition, you may ask the allocate 64 nodes in compact placement, which means you can get the full cabinet instead of having the nodes being spread around the full machine, so that you, only a few nodes actually located in the same cabinet. As you might know, each cabinet has full all-to-all connection, and it's considered your 0 full connect interconnect. And if you have 64 nodes located on the same cabinet, then your bisection bandwidth is highest. So for certain people who are reliant on all-to-all, all-reduce, or similar communication operation, that might be a performance changer. I just want to mention here that I personally do not use interactive jobs for a lot of reasons. We can have a separate discussion why I'm not doing that. I do not recommend using interactive jobs. I usually make the script and if I need to change something, I change the script, not typing. Maybe because I'm lazy also. But I've seen weird things when people use interactive jobs. And also there is one thing from performance perspective where people may forget that they have an interactive jobs and they just waste nodes. A little bit about the script that I usually use. As I said, I strongly recommend using model restore as your first command in script, simply because you want to make sure that your environment is pristine and it's always repeatable from a job to a job. For my own sanity, I always use module list as second command, so that my output always contains what was loaded, and if something goes wrong, I can quickly identify what was in my environment at the time of the execution. The third command, working directory, is usual. We require to do that just from PBS standpoint. We need to get the working directory and come into this. The job ID is required for the future reference. If again something goes wrong, that's how to get it. If you need to know your host name, that's the way to get it. If you need to know which node has been allocated, you need to parse the PBS_node file, environment variables. And now, interesting thing, there is no requirement to use the node file that is given to you as default. It is an expectation that this node file is sorted in some way, but there is absolutely no requirement to have this node files being sorted. It is quite possible that the node file is giving you a set of random nodes shuffled across the entire machine. So if you need to have a topology-aware simulation, and some people do those, for example, when you need to have two partitions in your simulation being tightly coupled, then it makes sense to connect those simulations close to the node locations. Then you need to work a little bit with a node file that you can generate, sort, split, and so forth. So here in the line 8, 9, 10, I show a little bit of how to just sort the node list and then execute using the sorted node list in MPI exec line 19. This is just an example. You can do more complex things depending on the workload you're running. Line 11, extremely important for those people who use multiple versions of different libraries. I myself use different MPH libraries, therefore, just to make sure I do not confuse myself, I'm trying to see which libraries I use at each time. Obviously, in line 11, you see a type, I will fix it later. And then the simple way of setting up the number of ranks, the number of nodes, the necessary environment variables. And I also recommend, if you set a certain environment variable, use echo to print this out later on so that you have a script of your execution. Finally, for CPU bind, we will have it. We have this discussion a little bit later. I always use --CPU bind verbose, comma, list with explicit statement of course and binding to MPI processes. I do not recommend using defaults, and I do not recommend using wide list or certain simplifications. The reason is that the binding of MPI processes to CPUs are so much important that it should always be explicit and should always be validated. And how to validate that? Well, that's what verbose CPU bind verbose command is about. So the verbose command prints you out the masks which are the CPUs from Linux standpoint, which are allocated to the process. And in simple situations, like in this example, when we have the single MPI process is allocated on one core, you will have a very simple mask, like in here, mask 1, mask 2, mask 4, mask 8. It is just a hexagonal representation of a single bit of a mask. I tried to make a little bit formal way of description of what the mask is. In reality, it is quite simple. The bit mask is just a continuous set of bits. If the bit is 1, then the core is allowed to be used. If the bit is 0, then the core is not allowed to be used for placement of the MPI process. That when MPI process is created, then all children of this MPI process will use the same mask. Therefore, if you use threads, for example, then you should allocate more than one core for the master MPI process. Then you will see the ranges, and then the mask will be more complete than just a single bit. So this is what I was trying to explain here on that slide. I hope this is not so much complicated. So this particular example is incorrect today. The reason is recently we have reserved the first core of each socket for system use. We have noticed that the system is using them excessively, and we don't want users to have significant degradation in performance when they place the user processes on those CPUs. Because of that, the CPUs 0 and 52, so the thread 0 of core 0 of each socket, and the CPUs 104 and 156, this is the thread 1 of core 0 and core 52, cannot be used through MPI. And if you do that, you will have the error which is printed out here. Launch failed on a node because you have fewer CPUs and depth. So if you have this, check your binding. You probably use the core 0 or the core 52 in your binding. Many people say we have GPU over MPI, we have GPU over MPI. What does it mean? So simply put, the GPU over MPI means that the programmer can use pointers to GPU device memory in MPI buffers. Or in other words, you can place your buffers directly to the GPU memory and use those pointers in MPI calls. Technically speaking, this is not required for programming. You can always move data in between host and device prior to MPI call, but it is convenient. And obviously, because it is convenience, there is a price to it, and the price is performance. So this is an example of how to use this feature. So I was trying to put it as simple as possible, removing certain things that might be necessary for the real programming. But what I do here is that with the help of OpenMP, I'm trying to check how many devices I have on the process. I'm enumerating those devices myself using the lines 14 and 15. I do it in round robin. That's line 15 says that I'm using the local rank to set the device so that the pair MPI process and the GPU device are located closely to each other. And then I allocate the host and device memory using the regular malloc or OpenMP target alloc function calls. Then place the data to the device using the line 30 OpenMP target memcopy, use regular broadcast and copy the device, the result back to the host to print it out. So the program should work in a situation when the MPI is set to be GPU aware. In this particular situation, the val underscore device memory was allocated on the device but used directly in broadcast. And you can use every GPU buffer with your MPI call as long as you use GPU over MPI, which is default in our environment. As I said, there is a penalty when you use GPU-aware MPI. And if you know for a fact that your code is not using GPU buffers in the MPI calls, then you can use an MPI underscore CVAR enable GPU variable set to 0. In this case, subtle startup mechanism will be different, and your MPI init time will be reduced. For many people, this is not very important, but for those people who have throughput computation where every single instance of simulation is a simple MPI command and the execution is very short, the time for MPI init can be important and substantial for the entire simulation of an instance. So if that instance is not using GPUs for MPI buffers, then the variable may help. Addition to that, there is another side effect of this variable. If you use GPU unaware version, then you can save a little bit from memory. Obviously, the MPI is using buffers for internal consumption, and if you use GPUs, then addition to that, it also uses intermediate buffers for CPU, GPU movement. And these buffers can be released if you don't need them. There are other considerations where GPU-aware MPI is important but takes resources. And if you have certain situations like this, please report to us and we can have a discussion. This is a very difficult topic and very hard to cover all the things even in single presentation. And particularly the problem becomes when people have very different requirements for their simulation. So keep in mind that there are lots of possibilities that can be done when you know what you are doing and you know how to use GPUs and you lack of resources and we need to squeeze the next bit out of it. Contact to us. NIC assignments. We already discussed that we have 4 NICs on a socket, therefore 8 NICs on the entire node. These 4 NICs are assigned by the MPI by default using round-robin assignment for only those processes which are located on the same socket. So it's quite important to understand that if you do not place the MPI processes evenly across entire node, you may not have access to certain NICs. And therefore, you significantly reduce the capabilities of off-node bandwidth. When MPI process does not use multiple NICs by default, it is possible to change it. Currently, what we do is we assign 1 NIC to 1 MPI process only during the time of the run of the entire MPI job. However, as I said, if you think that you need to have more NICs used by the same API process, it is possible to do so. Obviously, if you start using more NICs from each MPI process and you run multiple MPI processes on the node, then the link bandwidth can be a limitation. So you need to be very careful when you're doing that way. Of course, if you place more than 8 MPI processes on the node, that some MPI processes will be sharing the same NIC. And of course, it is very well possible to have NIC be in a contention. again, it is quite important to understand your application and how it is using the NICs and how it is using the and whether the application may afford sharing the same NICs at the same time. It's very hard to give universal suggestion of how the application should use NICs in your application. Of course, there are other considerations additional to just NICs and MPI process. Of course, we have GPUs, we have memories. All these are factors for optimal performance. As we already know, the sockets are connected by the UPI bus, and there are ways of moving data between the sockets using this facility. However, the UPI bus is fairly limited with bandwidth and may not necessarily be a performance improvement for your application. So again, each time when you think you need to use UPI bus rather than other means, you need to have certain considerations for that. Also, UPI bus has a relatively high latency, which is explained by the requirement of using atomic operations, which are quite slow on Sapphire Rapid. So keep this in mind. Obviously, understand that the cores must be connected in some way through a network on the chip, and each core has quite limited capabilities of using the connection. It is connected to the network on the chip. Therefore, this consideration of having a single core using entire memory or a single core driving entire NIC are quite important. A single core cannot drive the entire memory, and a single core cannot drive entire NIC. So you need to have multiple cores if you really want to drive the entire memory capacity, memory bandwidth, NIC bandwidth, and so forth. So you need to place more processes and use more cores to do so. Now I'm coming to a few benchmarks to demonstrate what I just said. So here on the slide, I show that when you use the host memory in this particular situation, and you use just one NIC and place more processes to this NIC, bind more processes to this NIC, then depending on the message size, you have significantly different latency depending on the message size you're using. So up to about 64 bytes, obviously that's a single packet and the number of processes doesn't really matter. The latency of each message is about 2 microseconds. That's consistent of what we expect from the hardware on this machine. So about 2 microsecond latency for a single point-to-point communication operation with very small message size. For large message size, the latency is becoming almost linearly increasing depending on the number of packets you've been using here. The buffer for message injection is usually about 64 bytes, so you will probably have a SAW type graph like you see here on the left side. I'm not sure that in practice you will be using a single NIC for your simulation, but just in case you need to have certain performance analysis or performance study, the environment variable fi_cxi device name equals cxi0 will bind all the MPI processes available with this environment variable to this exact NIC cxi0. We have 8 NICs, so cxi0, 1, 2, 3, 4, 5, 6, and 7. That's what could be used in here. Or you can use more than one CXI NIC device attached to the MPI process if you know how to use those and if you program them yourself. On the right slide, I am trying to show that if you use old A8 NICs, you will have almost linear increase in offload bandwidth. However, one MPI process cannot drive the entire offload bandwidth simply because it is attached to a single NIC, as I already mentioned. So single NIC bandwidth is about 2021, in a very good scenario, 23 gigabytes a second. If you start adding more processes on the socket, you almost double the available offload bandwidth on your application. Like in this example, up to 4 MPI processes, you can see the linear performance improvement for large message sizes. When I say large message sizes, I'm talking about 8 kilobyte and higher. When you start placing more than 4 MPI processors, then obviously the NIC will be reused by multiple processors, but the bandwidth will no longer be increasing. And here I wanted to show that it is not always the situation when having more processors actually increase the memory bandwidth. As you see here, the balance is quite important. If you have 4 MPI processors, you have each MPI process using individual NIC and not sharing it. You have the best performance for single process, single NIC communication operation. If you have 8 MPI processes, then 2 MPI processes actually sharing the single NIC. And again, because of the balance, you have the highest bandwidth in your example. So try to balance the number of NICs and the number of MPI processors you're running. And remember that because we have 6 GPUs and some people use them as 12 GPUs, then there is additional consideration of how to use 12 GPUs and 8 NICs at the same time and be in balance. So obviously you need to have not 12 MPI processors as most people do, but probably 24 or 48. This is example for device memory. This time I've been using multiple GPUs and they are trying to inject data through one NIC, sharing the same NIC through 3 GPUs on one socket. That's what the left slide is about. And as you can see here, even one GPU cannot saturate a single NIC. So we need to have more than one GPU sharing the NIC to saturate the bandwidth of the NIC. Placing two MPI processors and therefore using 2 GPUs at the same time significantly improves the memory bandwidth, moving the peak performance of a single link to about 128 kilobyte message sizes. Even more GPUs sharing the same link allow you to move the inflecting point closer to 64 kilobyte. Again, the single NIC allows you to get 23 gigabyte a second at best. The right set of slides is about placing the MPI processes on the same socket and using only 4 NICs with a round robin. This time, the multiple GPUs are sharing the same NICs on the same socket using multiple sockets, and therefore remember that all the NICs are sharing the same PCIe Gen 4, Gen 5 switch. So this switch needs to be used to convert the data coming from GPU memory through PCIe Gen 5 bus into the NICs sitting in the PCIe Gen 4 bus. We noticed that using the all 4 NICs from GPU memory is almost impossible with highest bandwidth of 100 gigabyte a second. That's what the peak performance of 4 NICs. and we are measuring performance at around 70 gigabytes a second at best. So the usual situation when people use 6 MPI processors is in a red slide over here, and it is not the best way of using the machine, as I already mentioned a few times. If you use 6 MPI processors on a socket, or in other words, 12 MPI processors on a node, you are probably reaching close to 60 gigabytes a second of node bandwidth per socket out of 100. So you're losing approximately 40% performance. A few words about the memory domains. This is a little bit outside of the main topic of this presentation. I'm not talking about MPI here. As I already mentioned, that we have 4 memory domains on a node. Two memory domains are assigned to DDR. 2 memory domains are assigned to HBM. And default memory domains are DDR. So you need to do something additionally to use the high bandwidth memory. There are multiple ways of using high bandwidth memory. I'm not coming into deep details of those. Just mentioned that there is libnuma, there is unified memory framework, there is memkind, multiple things. They're somewhat similar in behavior, somewhat different in the way of programming them, and each of those probably require a different presentation. So, and I've been thinking about doing that sometime in future. I'm not covering that. Just keep in mind that the memory domains are very important, and when you place your data, you need to know where to place and how to place. There are both memory capacity, memory latency, and memory bandwidth considerations. The usual NUMA-CTL command tool allows you to specify the memory bindings for a given MPI process. In this particular case, if you want to run your applications entirely from the high bandwidth memory, you might probably want to bind the memory domains 2 and 3 to your application. This is about the same that I just mentioned. The memory domains to the sockets are connected through a different bandwidth. Obviously, the memory, the regular DDR memory is slower than the NUMA HBM memory domains, about factor of 2 in our machine. So about 240 gigabytes a second. That's what you can see from DDR, and about 430 gigabytes a second when you access the HBM memory. There is a limitation when you access the memory domains through UPI from socket 0 to socket 1, and you can probably measure 110 gigabytes a second from HBM and 120 gigabytes a second from DDR, like mentioned here.
Vitali, we have a couple of questions. And I think it belonged to maybe a previous slide. So one of them was asking
This slide is designed to show you that the amount of available memory will depend on the size of the partition that you've been using. So by default, each node has 512 gigabyte of DDR on each socket and 64 gigabyte of memory for high bandwidth on each socket. And if you run a single MPI, a single node MPI process, you may expect that you'll get almost close to the peak availability of the memory, like here on the left slide for single node. However, remember that because we are not rebooting the nodes from job to job, you may face with a situation that the previous job left memory allocated, and because of that, your available memory will be not as you expect. So because of that situation, it's a good idea if your memory capacity limited it's a good idea to check how much memory you actually have at the beginning of your run. Another consideration is multi-node environment. And here on the right slide, you will see how much memory can be available through DDR when you use 12, 24, 48, and 96 MPI processors on a node using up to 2048 nodes environment. So the number of endpoints for the NIC interfaces is increasing. Obviously, for each node, you have at least 8 NICs, and the CXI provider on this machine is generating the tables for connectivity for each job individually when you launch MPI exec. To keep the connectivity of your job between NICs requires the tables. The tables obviously increase exponentially in size depending on the number of endpoints, and this takes place. That takes memory. We know about that, and one of the reasons we were trying to upgrade the environment on Monday is to fix this exact problem. So the problem did not disappear completely, but the amount of memory available on large size jobs is significantly better than on this slide. As you can see here, somewhere around 128 nodes with 96 ranks per node, you may have significant amount of memory pre-allocated before the user even have a chance to do something. So the typical amount of memory available to a user on multi-node environment is below 450 gigabytes per second. A few words about the local environment. I already used this during my examples. There are several variables that the Cray parallel application launch service is identifying during the launch of a job. All the variables that Cray launcher is making have predefined as pulse underscore. So the pulse rank ID gives you the job process ID if you need so. The pulse local rank ID gives you, sorry, not job process, the process ID. And then pulse local rank ID gives you the node process ID. So in the situation when you want to have a sophisticated assignment of your NUMA domains for the memory or your GPUs or NICs, and you want to fix, and you want to identify yourself on which socket you're running, these are the variables you want to use. And of course, if you want to have the shared memory used, then you want to have MPI the shared memory region through MPI standard, MPI shared memory region, you can use MPI COM type shared predefined. That's another way of using the locality of MPI to identify the placement of MPI processes on a node. This is a full example of how to identify yourself in the environment and how to identify the devices and locate those devices in a way that each MPI process will use the local GPU, the GPU located directly on that same socket. Keep in mind that this exact environment is using a non-standard, non-portable extension of Intel OpenMP runtime for devices and sub-devices, and also for the backend implementation of libopenmp target plugin, which is by default level 0, but some people may want to use OpenCL, which is also available on our machine. Many people are using the compact environment for placing the GPUs so that the GPUs are allocated correctly, and the official way of using it is to use Thomas GPU_tile_compact shell script for your MPI exec command. Not coming deep into the details, I present you what is this actually doing, and you can do your own way of setting the variable in a way that the GPU affinity mask is identified according to your need. You can do more complex ways of doing things if you do it yourself, as long as, of course, you understand how to do an assignment and how to make the correct identification of the placement of API processes within a socket and within GPU enumeration. Don't want to spend much time on that because this is all documented in our environment on the slide. So this benchmark shows you the approximate difference for the cost of a UPI bus. If you access the memory located on a different socket, then you will be using the UPI bus, and there would be a few atomic operations involved of making synchronization between the sockets. The cost for such access is about 1 microsecond. So we usually have about 0.8, 0.9 microsecond cost for the call of every MPI function call. Approximately 1 microsecond will be added if you use incorrect, or if it is by design, if you use access of a different socket memory. Of course, when you are memory bandwidth bound, then this difference can be increasing, but this has nothing to do with the latency itself. It is just a limitation of the bandwidth of the UPI. And finally, I come to the communication between the two GPUs on a node. As you already know, the GPUs are connected through Z-links. The links, which are about 20 gigabytes a second in peak. And our benchmark showed that if you need to move data between the two GPUs, you are capable to reach the 20 gigabyte a second per link bandwidth for significantly large message sizes. But usually when you start moving data in between the GPUs, you are about large message sizes anyway, so should not be a problem for you. The point-to-point communication operations use the links on a node automatically and is configured by default. So you will take advantage of moving the links instead of using UPI, as I mentioned on the previous slide, and have not only the full bandwidth of multiple the links, also lower latency. And then the same benchmark now when the data are coming from the NICs. This is the slide which shows how to reach the maximal memory bandwidth for multiple NICs on the device using very large message sizes. So it is possible to use about 180 gigabytes a second. However, it needs to be hidden in a way that the NICs should not directly inject data. Sorry, the GPUs should not inject data directly. There must be the PCIe Gen 5 interface involved. And finally, a little bit about collectives. So the collective operations is a very hard area and very difficult to cover it even in one presentation. The difficulty comes from the point that when you run a job, you get a very distributed set of nodes, and it's very hard to make the topology-aware collective communication operation in a way that it reduces the amount of connections. And frankly speaking, it is not necessary that the smaller number of collective point-to-point operations, collective means when each collective is designed through point-to-point communication operations, the total amount of point-to-point communication operations underneath doesn't need to be providing the best performance. In fact, it is almost never the case. So there are lots of different implementations for each MPI collective, depending on the message size, the number of nodes you have, the number of processes you have on a node, and so forth. Different algorithms can be used to improve performance of a specific collective. If you think that collective that you've been using is not performing well enough, then you need to talk to us and we may have a discussion of what can be done. In this particular slide, I would like to show the reductions for the latency from GPU devices for relatively small message sizes, in this case 8 bytes, 512 bytes, and 2 kilobytes. If you are a machine learning person and if you are using gigabytes of data, then you don't probably use MPI in the first place. You probably use 1CCL, and 1CCL is using an entirely different set of algorithm for communication. So they should not be compared with MPI directly. Keep in mind that if you use MPI and if you do reduction operation, then for small message sizes, the MPI underneath will not be moving data from GPU directly using RDMA. It will be using the data intermediate on the DRAM and then make all the computation for the reduction and the exchange across the nodes through the CPU memory. So 1CCL is doing different. And finally, for those people who use ALCF machines for a long period of time and know the IBM Bob Walkup's MPI profiler, it is here for you and you can use it. Here is the slide which shows how to do so. The final check. If you're happy with the result, just continue using the machine. If you are not happy with the result, then you probably want to know more about the domains of our machine, how the sockets are subdividing the devices, how the devices are shared, how to maximize the resource utilization and the balance of them, how to map ranks to the cores devices to ranks, memory to devices to ranks, and so forth, how to find yourself as an environment. Always do sanity check. Sometimes you may probably need to use an MPH debug module for debugging, which has debugging symbols. And obviously, if you have difficulties or see something which is abnormal or not matching your expectations, send a message to either support line, or many people are on Slack. So Slack is not recommended, but a possible way of communication. And this is my final slide. Thank you very much. And I'm happy to answer questions if they exist.
Thanks, Vitali. We did have a couple of questions. I think that was one is related to one of your slides, which I think we passed, but let me ask the other question. So Alfred is asking if NIC have its own memory separate from the other NICs on a node. Does a NIC have its own connection to the PCI bus or socket?
Sorry, Yasia, and it was a typo. By NIC, I meant socket.
Okay, so you meant socket. Okay.
Yes.
So you may want to just ask your question then.
Yeah, so does the socket has its own memory separate from the other socket on a blade? And does the socket connect to the PCI bus or whatever bus Aurora is using? I mean, what I meant is that the socket is kind of like an individual unit that you can almost treat the socket as a node.
Sorry, I did not hear the first part of the question. Can you repeat the question?
So does the socket have its own memory? That's the first question.
Okay. So the first question, the answer for the first question, each socket has 512 gigabyte of DDR5 memory, and 64 gigabyte of high bandwidth memory.
And does the socket have its own connection to the bus?
It
I
is,
guess they're for NICs, right? So, so maybe my question is actually might not be phrased correctly.
okay.
So the connections are conducted via the NICs, right? Not through the bus.
What do you mean, what do you mean bus? What do you call a bus?
So how does the socket, how is the socket connected to the other socket on the blade? Is it by a bus or I don't think that you connect two sockets on the blade by NICs, right?
So this is how the cores, so you have Intel Xeon CPU MAX series, which has 64 gigabyte of HBM2E memory inside the package, directly, right inside the package. But DDR5 512 gigabyte memory is connected through 8 channels over the network on a chip. There's no bus involved. If you are talking about the bus, there are two types of buses over here. The UPI bus, which is connecting the two sockets together, or PCIe bus, which is connecting external devices, such as NICs and GPUs. So the memory is not using any of them, except when you try to use the memory of socket 0 by socket 1. In that case, the UPI bus is used. Does it answer your question?
Yes, thank you. I just a conceptual question. Can I treat each socket as a node? I mean, does a socket actually can operate on its own?
Yes, okay, that's a very good question. So strictly speaking, the term node is used by the scheduler. So this is the minimum piece of hardware that the scheduler provides you as a user for a job. In that sense, a scheduler will always provide you entire dual socket system. So even if you do not use one of the sockets, you will be allocated the entire socket anyway, the entire node anyway. But practically speaking, yes, you can place all MPI processes on a single socket, assign all the GPUs of those sockets. There would be only 3 of them, apparently. And then you will be automatically assigned only 4 NICs on that socket, and you will have a complete environment, completely workable. You will be not using half of the NICs. You will be not using half of the GPUs. You can potentially use entire memory. You will have a penalty because you will be accessing this memory through UPI, but you can use it.
Okay, thank you.
The only thing is that I'm not really sure you want to do that, because if you really need to reduce the number of MPI processors for some reason, why not placing them on different sockets? Because you won't have any advantage of having them on the same socket. In fact, you will have a disadvantage because they will be using tighter connection between each of them. You will be bound by network on a chip bandwidth. So I would recommend using the balanced environment where both sockets are always used, regardless how many MPI processors you need. I presume you need always more than one.
Okay, thank you.
Oh, sure.
Thanks, Vitali. I know there was one more question, but that was related to a specific slide. So, Hari, do you want to say which slide was that your question related?
It is related to the GPU bandwidth. I think it's probably slide 10 or something, 10, 11. Yeah, that's one.
Okay.
So is that message size per GPU or is the total message size the x-axis? I was just wondering.
That's message size per MPI send command.
Right, okay.
Not per GPU, because to make that slide, I've been using multiple MPI messages outstanding at a time. But
Okay.
each message is that message size.
Okay, so is each MPI process bound to one GPU or is it like?
Well, on the left side, you have each MPI process bound to one GPU,
Yeah, okay, yeah, that's
and
it.
every MPI process bind to the same NIC.
Yeah, okay, yeah, thanks.
Thank you.
Mhm.
Are there any more questions for Vitali? Okay, if not, I would like to thank Vitali for this great talk and all of you for attending. We will be providing the slides and also the recording available on the website, and we'll send you guys a note when it's become available. Thank you all again.
Thank you.
Thank
Bye-bye.
you, Vitali. Bye.